as you know, in the Anderson model, normal fault, you have the main stresses, the sigma 1, the main stress is vertical, sigma 3 and sigma 2, the less and the intermediate stress axis are horizontal, and usually you can form a normal fault with a high, mm, uh, high angle attitude. So usually they should be inclined at nearly 60 degrees. This is a classical angle for normal fault, close to the surface of the earth. But as so in experiments, you can break some sample. You put sigma 1 here, and the two conjugate fracture made making an acute angle. So this angle should be more or less 30 degrees. So the dipping of the normal fault is usually around 6 degrees and so on. Because, as you can see from this picture of a confossen, when you move a surface with respect to the force or to the stress, the from horizontal, you move this surface in this way. The maximum shear stress, you can see the stress and the angular surface as a maximum shear stress in this position at 45 degrees with respect to the stress. But of course, the rock is made by uh, is not just pure material with no chemical composition. You have a friction, you have a cohesion. So usually this in nature, this angle is lesser than 45, and this is close to 30 degrees, right? Because you have also the competition in between the normal stress and the normal force, because at 45 degrees, the normal stress that is perpendicular to the surface is still very high, so cannot allow a good slip along the surface. Okay, and when we deal with a low angle normal fault, we means mm, that we have a fault dipping 10 degrees or 20 degrees, so in a very flat attitude. With a very flat attitude, you are in situation like this, where shear stress is too low and normal stress is too high. So it is for from a mechanical point of view, it is almost impossible to have a slip along a low angle normal fault. Low angle normal fault are, of course, very common in metamorphic core complexes. You have malonite like this, folded in an antiformal way with brittle fault above. So it is a big problem. Uh, so some people think about that normal low angle normal fault there were high angle normal fault then rotated. It is a good explanation, but it is not good for the South Tibetan detachment because it is quite flat, but it is flat all along the belt for more than 2,000 kilometers. So we cannot imagine a rotation of all the belt from steep altitude to flat altitude. So we can face the problem with other thinking to something different. Maybe some strain softening mechanism that allow the deformation to go along the surface, a flat surface. You can use fluids. You can allow the occurrence of leucogranites that are melted along the South Tibetan detachment. So they can allow deformation very easily, a mechanism of strain softening. Or it was before a flat thrust, and then they're reutilized as a normal fault. This is also another possibility to explain this strange attitude of the South Tibetan detachment. Here you can see a picture from the South Tibetan detachment. You can see leucogranite completely deformed, sheared along the detachment. You can see very well C plane, S plane, and in this leucogranite to the top, to the north, since the South Tibetan detachment system in the Rombuk Valley, in the north slope of the Everest, has been included in the first 100 International Union Geological Science Heritage Sites in 2022. This is certification by the IUGS. This is the proposal that we made with the colleagues Iaccarino and Montomoli. This is a picture of the South Tibetan detachment in the Rombuk Valley. This stuff is a leucogranite. The dark stuff are sillimanite grade mica schist, and these rocks are Ordovician rocks with fossils, are brachiopods, and so on. And this is one of the first sections that we put in the publication. This is the trace of the two strands of the South Tibetan detachment. This Mount Everest. This picture is from Courthouse and other 2016. On the F1 fault, the lower fault is a ductile one, and the blue F2 is the brittle fault that cross-cut the higher part of the Mount Everest. Here you can see two sections. This section was made in 1998. At that time, publication was in black and white, not color, unfortunately. But you can see here, this cross section was with the upper brittle fault here and the lower ductile fault here. Of course, this is a shared zone with a thickness of maybe 1 kilometer. The upper brittle fault is only a few meters or few uh, dozen meters, no more. This color section made by Mike Searle a few years later. You can see the granites here, deformed in the ductile shear zone, the so-called Chomolagma detachment from the Chinese name of the Mount Everest. You can see this dipping attitude became flat and flat here, and these two shear zone and the upper fault merge to the north, so that the Ordovician limestone that occupies the top of Mount Everest came into contact with the high-grade gneiss below. Here's just a picture from the Rombuk base camp. The distance is 30 kilometers, so this altitude is more or less 4,500 kilometers. The Chomolagma detachment here and the Lhotse detachment more or less in this position. So these are sedimentary rocks of the Tethyan realm. These are metamorphic rocks, and these high-grade metamorphic rocks. Here's another close view picture of the South Tibetan detachment. Here, Japanese geologist at 8,530 meters in the paper by Sakai and others 2005. This geologist reached the Chomolagma detachment. You can see here the breccias and the cataclysite characterizing the South Tibetan detachment. And of course, it was not the only one geologist almost reaching the top of Mount Everest, or close to the top. And since the detachment is deep into the north, we were able to intersect the detachment more or less in Tibet at 5,000 meters without climbing to Mount Everest, fortunately, unless we are not able to to take sample. Okay, this the picture that I showed you before. You can see a fossil, a brachiopod fossil here, just in these rocks that are dipping to the north. The detachment is more or less in this position. This is a leucogranite. Here the leucogranite, you can see here. In scene section, this is leucogranite show a very beautiful mica fish with the top to the north sense of shear, recrystallization of mica, recrystallization of quartz, brittle feldspar. Very nice characteristics of this picture. Here you can see the high-grade gneiss with feldspar, biotite, and sillimanite. This is black stuff here. And the Mount Everest is on the right. Okay, this is a sample took just from the outcrop. You can see in the cut beautiful mica fish, C plane, S plane like this, C prime, and this is just uh, LiDAR scanner of the sample. Here's the surface where you can see a little bit better the feldspar, the mica fish, this dark big crystal, the C structure, the S structure, the model one. In this section, you have a beautiful mica fish, this red one. So the sense of shear is very clear. There is a strong recrystallization on the rim of this white mica, and also on the tails of the fish. This stuff is crystallized mica. So yeah, some fish from the book Himalaya Dynamic Veggiant from Gruitz and Kellett. Maybe they made a chapter about the South Tibetan detachment. You can see very beautiful structure everywhere. C prime, sigma type porphyroclast, deformed leucogranite, deformed SC and mica fish also in section. So the sense of shear is quite clear. And it was discovered by Jean-Pierre Bourg in 1983 during the PhD, just in this outcrop. Because before it was considered only a trust by Chinese geologists, but it was the first to discover this normal sense of movement by studying the kinematic indicators. It was a good structural geologist, of course, one of the first. He was able to change the thinking of this very good fault. This is a picture made by climbers of the Chapungtang, close to 8,000 from the Nepali side. And you can see a huge seal of leucogranite here, gneisses intruded by this leucogranite, and the South Tibetan detachment are more or less in this position, and these low-grade sedimentary rocks. There are also samples taken from climbers that are in the museum at Oxford, I think, and some people studied also this sample in section. Okay, I show you that sometimes in the Mount Everest section you have a ductile fault and a brittle fault, but it is not so common all over the belt. For example, in this part, just north part of Mount Everest, you have biotite silmanite gneisses, the dark stuff, mycelium leucogranite here, and just above Ordovician limestone. So here you have not two faults, the tile and the brittle fault, but just one single contact of non-metamorphosed rocks above high-grade metamorphic rock. Of course, these Ordovician limestones are a little bit heated by the lower Glitterman sequence and show deformation at the base. This is a picture of the South Tibetan detachment at Mount Cho-Oyu. This picture was took by Fabrizio Bartoli, bachelor students in Pisa a few years ago. He was a climber and tried to reach the top. He was not able because problem of altitude sickness, but the colleagues reached the top and collected a few samples for us. And for example, at the Camp 3 at 7,800, 7,900 meters, we found a beautiful small sample with cataclysite. This is a scene section, and scene section you can see levels of cataclysite with grain size reduction by fracturing, characterizing the upper part with Tibetan detachment. There is also some small normal fault cross-cutting these levels, this cataclysite rich level. So very nice exposure. Associated to the South Tibetan detachment, there are sometimes huge faults. In this section, the Kaligandaki Valley, You can see the Annapurna detachment, the ductile part of the detachment, below the Great Himalayan sequence. Above you have Mount Nilgiri, and so on. And in the landscape, you can see kilometer scale overturned fold like this, folding the Devonian, Silurian, and Cambrian rocks, very well determined in this part of the belt. So the detachment causes a deformation, a folding deformation, um, overturned folds in the Tibetan sedimentary sequence with a north-east north divergence, of course. Is Mount Ukuche. You can see in this part this kind of fold related to the detachment. This is a reconstruction of the fold, the Nilgiri anticline, and in this mountain that's called Pangnap, you can see an interference pattern because this is F2 folds linked to the detachment, to the normal sense of shear detachment. And here you can see a previous fold related to the one deformation from collisional stage with top to the south movement and mm, fold reversed to the south. So there is a beautiful interference pattern in this part of the belt. So the first phase to the south and the second phase to the north due to the detachment. Okay, so we can give a look to the architecture of the detachment across the belt. Here we are in Dingye, south of Tibet. Is an old monastery destroyed by Chinese when invaded Tibet, and the dark stuff is made by high-grade gneisses, sillimanite, biotite, and garnet. The white are deformed leucogranite, and this is a breccia made of Ordovician limestone. So you have a ductile rock here and brittle rock just above. So these are clasts of the breccia made by Ordovician rocks, deformed by the brittle fall. Just lower, the leucogranites show the same face as all the shear leucogranites along the South Tibetan detachment with a beautiful shear sense indicators. In the mica schist, you can see more or less SC fabric to the top north sense of shear. In thin section, you can see mica fish like this, and this pole diagram, they are reported as the C-axis of the quartz that more or less indicate the same sense of shear. Mm. Uh, Here we are going to the base of the Tibetan sedimentary sequence with Ordovician limestones that became a little bit more recrystallized, so they are fine-grained marbles. And in thin section, you can recognize this calcite crystal recrystallized along this layer, making an oblique foliation like the quartz that you observed a few days ago. There are some porphyroclast, sigma type porphyroclast, magnesium enriched clast with a top to the northeast sense of shear. Here we are more or less in marble of the Kaligandaki Valley. There is a strong recrystallization of the calcite crystal with more or less ground boundary migration. There is an intrusion of leucogranites. The leucogranites are sometimes stretched and show budens or show some it's called a flanking fold. You can see here this fold above, this fold below. The fold is concentrated only along this piece of leucogranite. So they could be good kinematic indicators, but probably now it is dipping to the left, probably started dipping to the right and was rotated during shearing, causing also the formation of these drag fold that are confined only in this part of the layer. Also common this kind of picture. We are now in Garhwal, so in your country. There are some extensional shear band here, some myelonites here. We took a sample in this part and we dated. There are beautiful mica fish. We are in western Nepal, in Dolpo section. We found big leucogranite stretched and then rotated like delta porphyroclast. There are also some asymmetric folds related to the detachment and strong recrystallization of a calcite crystal, as you can see in thin section. Okay, in Western Nepal, in Kaligandaki Valley, Laura Nania made her PhD thesis with Chiara Montomoli a few years ago and published 3 papers. Now she's working in Geological Survey of Canada. And here we can see in green the Greater Himalayan sequence affected by the shearing of the South Tibetan detachment. In light green, the deformed part of the Tibetan Himalayan sequence. So the South Tibetan detachment affect both the bottom of the Tibetan rocks and the top of the Greater Himalayan rocks. The problem that you can see here, there are marble, 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 marble. You have marble of the Greater Himalayan sequence and marble of the Tibetan rocks. So it is very difficult to detect the formation, the sense of shear. So we have uh, also in thin section. The same happened in Western Nepal. We have marble and silicate of the metamorphic core and the marble of the upper sequence. But we took several samples in a vertical section. Also, you can see another feature. In thin section from the upper part, this is more or less, I think, 800 meters. So the grain size of the calcite is, if you go down, 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 the grain size increases. Do you remember the granite in the Alps with the work of Michael Stipp showing mechanism of quartz? It is more or less the same. It is not a simple granite, but a very hot unit. But the grain size of the marble increases a lot going down up to the boundary with the Greater Mayan sequence and also inside. So Laura was able to do a very nice work with calcite. Calcite is not so easy as quartz to work with, but he spent several months at the George August University in Germany with Bernard Delace and Chiara Montomoli, working with these rocks. He made the analysis of the C-axis, the y-axis, different axis of the formation of the crystal. So we detected also the occurrence of twinnings in calcite. So from this kind of graph, people are able to build up the sense of shear uh, and also the amount of pure shear and simple shear. It is not easy and I cannot explain because I need 1 week more to explain this complex. But anyway, there is a paper Nania and others 2014 Tectonophysics and 2022 on Journal of Structural Geology that explain very well this kind of work. So for from the fabric of the stereographic projection of the C-axis of calcite, we were able, using the Wenck diagram, to detect the amount of simple shear, pure shear. We have several samples approaching the South Tibetan detachment, going down, the simple shear increases in this way. In this kind of graph, there is a percent of pure shear and kinematic vorticity, and also in this case, from the more distant upper portion, going down, 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 the simple shear increases derived from this kind of complex calculation by z-axis of calcite. Uh, the, so this kind of work was made in Western Nepal, Central Nepal, and Southern Tibet. Along this section that we collected several years ago. So approaching the high strain zone, more or less the meaning of this graph is that approaching the high strain zone, the non-coaxial deformation there is a non-coaxial deformation, but there is an increase in simple shear up to 70%, 75%. So from pure shear dominated deformation up to simple shear dominated deformation. This by calcite fabric. We can use also grain size to gain information about the differential stress that deformed the rocks, because as you know, deformation characterize a decreasing in grain size, so much more stress produce finer grain size. So the grain size is related to the differential stress. So if you take the thin section and you made some measurements of the grain size, the medium grain size. You have, for example, in these samples, the mean grain size is 310 micron. In this sample, it is 420 micron. So you can detect in a quantitative manner the increase of grain size, and you can use this information to characterize the differential stress using some because of the piezometers by Barnhorn and other 2004 useful for calcite. In this equation, the logarithm of stress is linked to the grain size d. So if you have the grain size, you can more or less calculate the amount of stress that cause this grain size. And for some sample is from 5 to 15 megapascal. And if you are able to detect the amount of temperature, you can also fix the strain rate, the amount, the velocity of deformation. The strain rate has been fixed by more or less calcite dolomite geothermometers or by the mechanism of deformation of calcite. So putting 400 degrees, you have the differential stress here, and you have this line that characterizes the strain rate. It's not so easy, but more or less Manaslu Valley, Kaligandaki Valley, Lower Dorpo region concentrate in this part, in between these two lines. Another important feature that you can see an increase in grain size of the calcite. So there is a dynamic recrystallization with grain boundary migration and so on. But above this big crystal, you can also observe some twinings. Okay, and these twinings characterized by calcite, called E-twins, but I cannot go in detail. Increasing in the width of the twins and the density decreasing towards the bottom of the shared zone. This is the bottom of the shared zone. So the grain size increase the width of the twins, and the density is became lower. You can see here a higher density of twins, here less density of twins. So uh, you can use these twins to detect the shear stress. There are some methods by Rebaki and others 2011, a piezometer. So you can assess the amount of stress necessary to to determine this kind of deformation that is quite a brittle deformation. Do you remember? It is a brittle ductile deformation, and by this density of twins, you can assess the amount of stress necessary to deform. That is 110, 170 million years, say million years, megapascal, sorry. And it is quite higher with respect to the stress calculated to determine the grain size. So it is necessary much more stress to cause the calcite than to cause ductile deformation. There is an explanation for this. Our explanation is this one, that deformation during the South Tibetan detachment can be characterized by two stages, the D2, we call D2 early and D2 late. You can see this line, this the Bayerly law for calcite, this exponential law for calcite. Every mineral has a different position of this line. For calcite, this one is the differential stress, the amount of stress, this the depth. So you are here in a brittle condition. This is a brittle plastic transition for calcite. Of course, for quartz or for feldspar is different. Could be in different shape. So more or less the meaning is this one. In the D2 early, when grain size increases towards the bottom of the shear zone, you need 515 megapascal to deform calcite because we are in this part of the line. So if you go here, you can find 515 megapascal. There is not the scale here, but the meaning is this one. If you approach the brittle plastic transition, this line move in this way. So in this part, to deform calcite bearing rock, you need much more stress. In fact, we found 120, 170 megapascal of stress. And this is more or less the strain rate. So the meaning is this one, that the deformation concentrated in the marbles in a ductile way, and the rock at the same time moved because we have a normal sense of shear. So the footwall of the rocks, the deformed rocks, moved upward toward the upper structural level, decreasing temperature and decreasing pressure. So from very nice ductile condition, they move in this part in the brittle plastic transition where they need much more strain to deform. There is a strain hardening. So the strain increases, the stress increases from 15 to 10 times more, maybe 150 more or less. In this way, you are able to deform the calcite, but not by crystallization, but only the formation of twins. And this was made to explain why there is not the brittle fault in this portion of the belt. Because in Lower Dolpo, Kaligandaki, Dinghie, or Marziandi Valley in Manaslu area, you have mainly the brittle portion, the ductile portion, but not the brittle portion as a Mount Everest. And probably it is caused by the kind of rocks because you have a lot of marble and calc silicate, and you can have not a so strong strain hardening because if you have strain hardening, the deformation cannot go away and the deformation jump to another position to deform the brittle fault. In this way, the formation was able to continue among the same levels of the shear zone by deforming in a different way. So this is a possible explanation of this difference along the belt where in some place you have the ductile and the upper brittle fault, but the rocks are different. You have not calc-silicate, but you have gneiss, granites. When you have calc-silicate rock, you have a different behavior, and the South Tibetan detachment it is developed only in the ductile deformation and in the more brittle deformation, but inside the same shear zone. So it is actually the only one explanation that we found for this different behavior of the detachment all along the belt. So in this way, in this portion, since there is a lot of marbles, we are obliged to use different methods. And of course, we use the calcite with this strange kind of feature. But anyway, the calculation of the position of a C-axis was made by a textural goniometer, so was made automatically, of course, because doing by hand, it's very, very, very time consuming. Okay, so just an example how to work with different rocks. So it is not necessary to go inside the method, but keep in mind that if you face this problem or similar problem with different rocks, there are the possibility to face these problems following this way. Okay, just a few words about the geochronology. Um, we use uranium, thorium, lead on monazite by in situ using laser ablation. This sample is from Garhwal, okay, from Garhwal, India. So these monazite are very nice. The blue color is low yttrium, the red color is high yttrium. So if you date in the core of the rim, you have different information. And we add the ages by 20, 19 million years that are retrograde ages with garnet plus melt has been consumed, and the yttrium has been released and concentrated along the rim of the monazite. So more or less these ages could be linked to the um, uh, ductile activity of the South Tibetan detachment. We had also some ages by Argon Muscovite by Montevagni, published in 2018, and the ages of Muscovite are more or less 16 million years. After that, at 14 million years, there is a growth of the static white micas in the same way to what happened in the main central thrust. So the South Tibetan detachment ended the deformation stopped before 14 million years because you have static micas above the myelonitic foliation. So in Garhwal, the formation is from 20 to 15 million years, more or less, of the South Tibetan detachment. This is a very hot deformation because we are above 500 degrees. This deformation is a little bit at a lower temperature, maybe 400 or 350. So if you remember more or less the ages of a main central thrust, 10, 9 of the Vaikrita, 5 of a Munsari thrust means that in the same transect of the belt in Garhwal, in the same part of the belt, the South Tibetan detachment is a little bit older with respect to the main central thrust, that is in between 9, 6, 5 million years. So they are not contemporaneous. So the South Tibetan is older and the main central thrust is younger. So they cannot act at the same time. And this is a problem for all the tectonic model that should be that needs the contemporaneous activity of these two folds. Okay, another problem for the South Tibetan detachment for the ages is this one, the Buraburi granite that I showed you before. Is cross-cut the South Tibetan detachment here because you can find this granite in the Greater Himalayan sequence here. and in the Tethyan rocks. So it is a pin in the South Tibetan detachment. It is undeformed. We gained the ages of the granite by using monazite and zircon, and the age was more or less 23.5, 24.5. Very nice ages made by Daniela Rubato when he was in Australia, at Canberra. And the main granite, okay, the main granite is more or less 24 million years, and there are some dike, including this kind of dike, including the Tethyan rocks, are more or less 23, 25 million years. Okay, you can see a picture from the granite below, the sedimentary rocks. These are dikes emanating from the granite and intruding the South Tibetan detachment. This is a picture of the leucogranite dike intruding the metasedimentary rocks of the Tethyan sedimentary sequence. This dike has been dated at 24 million years. So there are the rock around are really sedimentary rocks. You can see cross bedding. This level is rich of remain of fossils, Lumacella. And also we gained the age of the sediments by detrital zircons that give minimum depositional age. Anyway, we found ages around 100 and 180 million years. So since these sample are quite close, we put the occurrence of some faults like these, faults and refolded faults, then intruded by the Buraburi granite. So this is really the Tethyan Himalayan sequence, low grade, the ages, and below we have the greater Himalayan sequence. So the age of the South Tibetan detachment should be older than the age of the granite, so older than 25, 20, 24 million years. In this section, the main central thrust activity has been dated at 19 million years by Gibson and others 2016, and 17 million years by Montomoli and others 2013. So the South Tibetan detachment is 24 to 30 million years, and the main central thrust is 19, 17, 13. So very different, very distant ages. That is a confirm that they are not contemporaneous, at least in this part of the belt. So to conclude something about the South Tibetan detachment, we have a complex architecture of the South Tibetan detachment along the belt. Of course, we could expect this because it is very long, very big structure. Moving from east to west, the ductile branch is better expressed. Structure evolution of the detachment. Oh, okay, this is lacking something. There is a plastic deformation protracted at shallow crustal levels that prevent the detachment strain hardening. Uh, so we have deformation, ductile brittle deformation inside the marbles. So lithology variation along strike affected the overall architecture of the shear zone. Marble allow the development of a shear zone ductile and brittle, where you have granites, orthogneisses, mica schist, migmatites. You have a shift in deformation ductile below, and a shift jump to higher position for the South Tibetan detachment. This is common in the eastern part of the belt and also in the North Himalayan gneiss dome. For example, the Kangmar dome of Yalazambo dome, they have a brittle portion and a ductile portion below with the same characteristics. The deformation of a South Tibetan detachment is characterized by no coaxial flow, as determined by data also authors such as Rick Lowe, Don Kellett, and also our works. But there is a strong component of pure shear. Of course, pure shear decreases towards the high strain zone where simple shear became dominant, as we can expect. One of the important consequences about the geochronology it is that along most of the study section, MCT and CDS are not coeval, and the diachronicity of MCT and CTDS along the same sections and the occurrence of top to the south compressive high Himalayan discontinuity could suggest that South-Tibetan detachment activity occurred in pulses. So you have ages older than 24, ages 20 million years. So it means that this kind of fault was active in different portions in different times. So now we give a look to the high Himalayan discontinuity in the core of the Himalayan belt. Have you some question about this? This.
I just want to know that in Bangladesh there is one drone structure that is known as Leopard. I was reading that paper. That it was saying there is a shear flow which is Leopard shear flow, and it is being cut by the fault that is known as Colstrong fault.
Mhm.
The question is how this shear flow converts itself into a brittle fault structure. Is it a different phases of deformation taking place in that region? And
So, yes, there are some paper by Mike Jessup on the Pargil Dome, but I don't remember the ages of the deformation. But I will give a look. Thanks. It's very nice dome. Maybe it is linked to the Karakoram fault also. The extensional jog of the Karakoram fault. So maybe there should be an interaction between the Tibetan detachment and this dexter strike slip of the Karakoram. So I'm not sure if you can compare exactly the ages and the fissure in this part to the other.
one question is like how the shear flow translates itself into a brittle fault.
How? Uh, I will give a look to the paper. Thanks. Okay, now we give a look to what happened inside the grid variant sequence. Up to now, we worked on the boundary. Now we go inside. You remember this picture? You have a big shear zone cross-cutting the lithosphere. You have myelonites in the ductile portion. Uh, and the fabric in myelonites give information about the kinematics, of course. You remember kinematic indicators, the mechanism of deformation, flow type, simple shear, pure shear, deformation history, and PT condition. If you have the growth of a metamorphic mineral in that type condition, you can reveal completely the PTT condition of the formation of the shear zone. For example, here from this paper with Jain 2014, we have the growth of white mica and biotite. Here, the rotation of garnet. So the mineral give very useful information using hydrochemical pseudosection. You can precisely detect the PT condition. But if we deal with a regional scale shear zone, that means shear zone that have duration of several million years, and with amount of displacement of a dozen to 100 kilometers, we could expect an interaction between metamorphic condition in the hanging wall and in the footwall shear zone. So there is not metamorphism and deformation, but deformation causes an alteration of the metamorphism, affect the metamorphism of the rock below and above. So long-lasting shear zone can affect the metamorphic paths of the displaced crustal portion in the footwall and and the wall. And in this case, we speak about tonic and the metamorphic metamorphic discontinuity. And this term is intended to be comprehensive of both tectonic feature, including ductile and or brittle zone and the related kinematic indicators, and detectable metamorphic differences between hanging wall, foot wall, triggered by the discontinuity itself. This is a definition that we put in the paper by Montomoli and others 2013, where we firstly published the occurrence of the high Himalayan discontinuity. This is a definition used by the Commission of Tectonic Structure Geology of International Union of Geological Science. So with the tectonic and metamorphic discontinuities, we have to use different approach, structural analysis, geometry and kinematics, the petrology. You can see here the growth of garnet in section with chemical analysis and zoning in some minerals, for example, in some element, iron, magnesium, and so on. And you have to also to mix this information with geochronology. So in this way, you can gain the maximum information about the study of the of deep seated shear zone, long lasting one. Okay, and we started to study the Himalayan belt along several transects since maybe 2010. First time that we found this kind of discontinuity was 2010 in Western Dolpo, Western Nepal, lower Dolpa area, but we really do not didn't understand the meaning of this shear zone. So we need several years to try to understand what is the meaning, the age, and the consequences of these shear zones that we found in Western Nepal. We were looking for the formation of the South Tibetan detachment, but we crossed of the belt from Lesser Himalaya to Greater Himalayan sequence, and we found this shear zone in the middle. What is this? Is it detachment? No, the sense of shear is not right. So it was a little bit tricky, and but it was nice to go through this problem. So at the end, we were able to trace this discontinuity from northwest India, western Nepal, central Nepal, Sikkim, Bhutan, for then more than 1,400 kilometers. So the, this stuff is a Great Himalayan sequence. This is a higher Himalayan discontinuity here, traced from our paper, our detailed work in the field, but also from literature. And so it divides the Greater Himalayan sequences, an upper portion enriched in migmatitic rocks, and the lower portion that is made mainly by kyanite, garnet, bearing gneisses and mica schist. This is a geological map that we made in western Nepal, in the Mugu Karnali area. This is a Mangri shear zone, our local name. The gem shear zone was just in this very thin portion of the Greater Himalayan sequence. You can see this in this area, the thickness of the Greater Himalayan sequence is very high. In this part is very thin, only 3 kilometers. So there is a strong local longitudinal variation along strike of the thickness of this shear zone. In the field, for example, in Mugu Karnali, we found 3 or 4 kilometers of myelonites. We walked one day in the myelonites. In western Nepal, in the Tojem shear zone, we observed a lot of rotated porphyroclast also at the autocrop scale. In this geographic projection, you can see the shear plains deep to the northeast. The red dots are the stretching lineation. It is plunging to the northeast. And the sense of shear is thrust sense top to the southwest sense of shear, similar to the main central thrust. In thin section, there is the growth of sillimanite along shear plains, and you remember this picture. there is a grain boundary migration in quartz, a mechanism of deformation at high temperature. There is chessboard extinction, suggesting temperature larger than 600 degrees, so very high temperature shear zone. These are some feature at the outcrop scale, at the macro scale. This is the Badrinath shear zone that we found a few years ago with the PhD thesis of this girl, Beatrix Benetti. She tried to compare the Himalayan belt with with the Brazilian belt in Brazil because she came from Brazil, but his PhD was affected by COVID, so it was a problem to go in the field. But anyway, we took sample before of the Badrinath shear zone. This is this is an outcrop of the Myelonite and the Badrinath shear zone in the road going to the Mana last village. Scene section with the top to the south sensor shear. And now I show you the last example of the high Himalayan discontinuity in the Annapurna Manaslu Massif, in the Marsiandi Valley. In this map, you can see the South Tibetan detachment, Tibetan rocks, sorry, greater Himalayan sequence like this. This is the main central thrust. And here in the middle, we found this shear zone that is just in Jagat village here and Jagat village in the other valley. I don't remember the name of this valley, but there are two parallel valleys in the Manaslu Massif, and in the same village there was the same Myelonites. I don't know. It was strange. This is a thrust sense shear zone. There are beautiful kinematic indicators at the mesoscale, especially also at the micro scale. So the sense of shear is the same. The foliation is dipping to the northeast, and the stretching lineation is plunging to the northeast, as in the other shear zone. Another feature that we found in this kind of shear zone is that the PT condition of the footwall are always a little bit higher in pressure with respect to the one of the hanging wall. So there is a difference in 2, 3, maybe 3 kilobars between the rocks below and the rocks above. And the most important thing that the Malionic foliation develops under this part of the path, and the retrograde part of the path. So during the formation of the foliation and the movement of a shear zone, there is a decreasing in pressure. So there is an exhumation of the rock. It is testified by the PT condition detected. This is just one example of pseudosection in Western Nepal. So it's a very complex way to calculate PT condition, but very make some map of the minerals along the thin section and with some complex software, we detect path, the path followed by the rock. Some constrained here, the complete path is an example. Okay, and at this point we would like to know the age of this shear zone. So we use the monazite, as you could do before. This is a synthesis of the uh, Eigerman discontinuity in Marsiandi Valley. You can see some biotite, some SE structure. So it is show it up to the right sense of shear. We select the monazite under optical microscope. Then we go to the electronic microscope to detect if there are true monazite or zinc or some other things. This is the monazite. Then we made chemical maps of monazite. This is an yttrium, an example of yttrium map. Blue, low amount of yttrium. Red, large amount of yttrium. The core is depleted in yttrium. The rim is enriched in yttrium. So when we went to laser ablation in Santa Barbara, in California with John Cottle, the famous geologist, geochronologist studying the Himalayas and Antarctica. So you can see here the holes left by the laser to catch the plasma to make the attention. So this point for dating were selected just to date the core and to date the enriched yttrium of the rim. Why we use this kind of rock, of methodology? Because yttrium, thorium in monazite and garnet are a proxy of the formation of metamorphism. So during progressive metamorphism with the growth of garnet, all the yttrium is sequestrated by the garnet, and the yttrium is show very small amount of yttrium. When so the garnet grow and sequestrate of the yttrium. During the retrograde path, during breakdown of garnet or uh, some other things, yttrium is released in the rocks and is captured, sequestrated by the contemporaneous monazite. So a good monazite could show a core depleted in yttrium and the rim enriched in yttrium. This part is related to prograde metamorphism, this one to the retrograde path. So when we date this part, we are dating the prograde metamorphism. When we are dating this external part, the rim, we are dating the retrograde path of the rock, of the monazite and of course of the rock. So we made this kind of work for several shear zone along several transects, and more or less we found sometimes more complex behavior of the monazite because this one are the perfect monazite, but there is mm, some cases where you have a resorption of monazite, new growth, resorption. So sometimes the pattern is not so easy, but if you find some good crystal like this, you can gain the information. And the ages that we found with this methodology, uranium lead thorium on monazite is 25 17, 26 17, 25 18, 27 17. So they are more or less the time span of the age of the HHD in central and western Nepal. We use different laboratories, sometimes in different times, of course, Australia, USA, or a laboratory uh, in northern part of Italy. Now we have an instrument just in Turin, and we are just starting to work with this laser ablation and ICP-MS in these days. So in the future, the next month, I think we are able to date a lot of rocks. And if we compare the age of the main central thrust and this HHD, high discontinuity, we find that along the same section, the HHD is older than the main central thrust, because sometimes in the literature they are confused. Mm, If you make not a distinction between these two shared zones, sometimes people put all together or confuse the main central thrust, especially when they are very close. There is not so much distance in between them, maybe 100 meters or few kilometers, such as in Dolpo area, where the thickness of the greater Mayan sequence is only 3 kilometers. And so in these cases, we are able to separate the HHD, that is older with respect to the main central thrust. Okay, I can show you some details of the dating of the monazite. In this graph, there is the number of, uh, of data, and here the age. In red, the prograde path of the monazite, in green, the retrograde path. This is upper GHS, one sample. This is one sample along the HHD in the myelonites. This is so the difference in between the prograde and retrograde part is 28 million years, is 25 million years, and more or less this is the age of the HHD. But if we put all together, this graph is by our data and the data by Jamie Wang and others 2018. We can put here the HHD, here the retrograde ages, retrograde ages in the hanging wall and the upper part of the shear zone. If we go down in the footwall, you can see the prograde ages and the retrograde ages. What is the difference in between these two parts of this picture? There is a difference. Is a blue color and the yellow color are separated here, and in the footwall it is here. This is more or less 26, 27 million years, and this there is a shift of at least 10 million years in the footwall of this passage. So the rocks above and below uh, didn't underwent exhumation at the same time, but exhumation started before in the hanging wall and later in the footwall. This is the main meaning of this kind of graph. And what is why there is this strange behavior? Because usually people think about the occurrence of the main central thrust, and all the rock of Greater Magellan sequence were exhumed. This part we have the hanging wall exhumed before and the footwall later, 10 million years later. The cause is the occurrence of this shear zone, of the HHD, because as a kinematic like this, the footwall, the hanging wall move to the south and the footwall move to the north in different way. So when we activate this shear zone, the rocks below from B1 go to B2 in a deeper position. So from this position, they increase in temperature and pressure and go to B2. But the rocks in the hanging wall are exhumed because you can see the arrow. These rocks are brought to the surface. So a rock from position A1 go to position A2. From A1 to A2, there is exhumation, development of foliation, decreasing in pressure and later in temperature in this time span of activity of the shear zone. So this different behavior in the hanging with the footwall is caused by the activity of this shear zone. So up to, from the collision up to 27 million years, it is all right. But at the 27 million years, by the activation of this shear zone, there is a different behavior of the rock above and below. The rock above are exhumed, the rock below continue to go downward because of this error, because of the kinematic. This rock upper and this rock down. It's okay? So we need a lot of years to understand this, but at the end we found a solution. Okay, numerical models. I give you the information that the Monte Mason were able to build up some numerical models to explain the orogenic the origin. And so several years ago we asked, is it possible uh, to make numerical models? The numerical models will show only channel flow, or it is possible to show also the occurrence of some discontinuities, such as the HHD. So Andrea Piccolo was a master student in Padova with Manuele Faccenda, that is very strong in this numerical model, and he tried to build up several models to explain the convergence, collision, the strain rate, the PT path of the rocks. So he made hundreds of models. This is more or less the movie of one of the models. You can see several points indicating rocks going down in subduction, then coming up by corner flow. And so you can follow the PT path. Of course, this is a very complex model, not easy. So the dark, no, I would like to stop. The dark point, go down to the right. Okay, at this point, there is a situation in which these rocks are going downward and these rocks are going upward. So it is not a very precise model because uh, it is not possible to detect very thin characteristics, but more or less you have an asymmetric origin. This is a Tibet, very hard part. The origin is developed only on the southern side, the Indian side. There is the frontal belt, there is a strain rate, the PT are comparable to the one that we detected by PTT condition. And in this way, by rock moving upward and rocks moving downward, it is possible to think about something too similar to the HHD. So that, oh, this 80 kilometers, more or less, in this model, but of course it is not the only one. We are interested in try to think if it is possible to create a different model with respect to the channel flow. It was very complex because there were a lot of thousands of nodes in the model. So to run a model like this, maybe 8 to 9 hours of parallel computer. They rent time in at the Ministry of Research because they have the facility of this kind of things. So we are happy because it was possible. Then there are other numerical models made by Indian geologist Maiti Mandal, published in 2021, and they were exactly able to create, to build up the occurrence of HHD in the Greater Himalayan sequence. So I was very happy for this, of course, because as you told you before, in the channel flow, the Monte Jamaison forced the condition. You have a rigid upper plate and a rigid lower plate. You put material coming from India with heating from radiogenic mineral. So you melt, but if you are confident that this melt, the melt of course could move to the south. But if you change a little bit the standard condition, you can build up different origin, different exhumation models. So it's very nice. It's very complex, very complex, but very nice. So of course, Naiti and Mandal compared with the ages of of exhumation, South Tibetan detachment, HHD, main central trust, PT condition. So it's a very nice but complex paper because numerical models are usually very complex, especially at the scale of the origin. So at the end, we can say that HHD is a tectonic and metamorphic discontinuity lasting at least 10 million years, or 27 to 17 million years, which geometry and kinematics affect the PT path of the rocks in the hanging wall and the footwall. In Western Nepal, we found also a granitic dike cross-cutting the myelonites, and we dated this undeformed dike at 70 million years, 16, 70 million years. So at 60 million years, no more deformation along these myelonites, like the static mica in the main central thrust or the South-Tibetan detachment. Petrochronology allowed to recognize the PT paths of the rocks in the hanging wall and the footwall that are diachronous, show diachronous prograde retrograde paths because of the occurrence of this thrust sense shear zone. So if we would like to build up a simplified model of exhumation, up to 28 million years, the rock of the Great Himalayan sequence underwent under thrusting, increasing pressure and temperature. At 28 to 27 million years, up to 17, there is activation of this shear zone, this shear zone in the Great Himalayan sequence. So, whereas the lower part of Great Himalayan sequence continue to went downward, the upper part changed the path and was exhumed, started to move upward. So there is first the exhumation of the higher part of the greater remnant sequence, and then at the time of activation of the main central thrust, where this upper shear zone HHD stopped, the formation shifted at the level of the main central thrust, 17, 13 million years, 5 million years. At this time, also the rocks in the footwall changed the path and they started to be exhumed. But since this rock exhumed before and this later, we can detect a difference in pressure in between the rock in the hanging wall and the footwall. You remember this graph? Usually in the footwall, we record higher pressure with respect to the hanging wall. That is quite common all over the section. And this could be explained by this model. Okay, if we join the information because we are dealing with main central thrust here. Main central thrust, I show you that is made by Vaikrita and Munzeri thrust. I show you already this one, and the formation one after the HHD localized along the Vaikrita thrust at 10, 9, 8 million years. Then the formation stopped at 7, 6 million years because we have the static growth of mica on the myelonites, and the deformation shifted to downward towards the Munzeri thrust nearly at 5 million years. So there is a shift of the formation from the higher parts to the lower parts, dated by precise geochronology. And if we put all together, including the Badrinath shear zone, Badrinath shear zone has been dated at 23, 21 million years because our monazite was not able to catch all the history of a shear zone, because in some other places monazite catch the history from 28 to 17. This we are a little bit unlucky, so but more or less the age is the same, but we put what we found, 23, 21. So from collision up to 23 million years, all the rocks were put downward. Then the Badrinath shear zone of the HHD shear zone all over the world, the Himalayas, sorry, started to move. Of course, to exhume this higher part of the rocks, you need erosion, so monsoon, or activity of the South Tibetan detachment, some activity, because you need to put away some rocks above, because only by thrust you cannot exhume. You can to help to be helped by erosion or normal faulting, and then the formation from 20 to 8 million years shift along the Vaikrita thrust, then along the Munzeri thrust. So this is more or less the history that we can build up by HHD, main central thrust, and so on. Okay, this picture not from the Himalaya, but from the Western Alps. Okay, have you some question about mm, this topic, this HHD and the last model? Of course, it is quite it is simple, but it is complex because uh, it involves several sections, several methodologies. So you have to work with other scientists. So collaboration is very important because one single man could not do all this all this work. It is just difficult to follow one topic. To follow two or three topics, it's impossible because you have to read the book, paper, and so on. But with collaboration, exchange of thinking, opinion, discussion, it's very, very useful to find a possible solution. Okay. Oh, the method that I mentioned before you, it was tomography, microtomography, because with microtomography, the same that we use for human body, we can put in a small machine some sample, and by several section by X-rays, you can detect the shape of the porphyroclast in 3D without cutting the rocks, and automatically they calculate the orientation, the shape, and we made this kind of work in this paper 2020 on Terranova, because in Milan, the University of Milan, they have a micro CT, just put on the table, you put a small sample, and after a time they give a result of the 3D organization of the structure. And it's very nice because it's not time consuming. You have not to put lines to detect limits and so on. Uh, you need to have the machine, of course. The problem is that the samples that you put are very small, so you should have a very small porphyroclast. You have a big porphyroclast, you can only put one and so on. Okay. I will give you also some reference paper like this. I have the PDF. I send it to Mahesh, so you have some reference material. And so this after lunch, we are almost less. Okay, we can stop. We will discuss a little bit recall of the model of exhumation, the Himalayan belt. Then we speak about vorticity with an example. Then at 4 o'clock, certificate. It's okay. Have you some question? Feel free to.
But for normal fall along the way now. But along translating on it.
Hmm.
So what is the reason for
The reason for the formation of the attachment of the normal fault.
major plus away from the
But do you mean the South Tibetan detachment?
away from that right hand venture.
Hmm.
So we have normal fall along these plus also.
Ah, at the level in the lower part of the. Okay, there are some possible fault are transverse fault that cross-cut, for example, the main boundary truss, main frontal truss. People found this kind of fault also in the Mount Everest area, transfer fault perpendicular to the belt. There are a lot of these with cross-current movement. And of course, the activity of South Tibetan detachment ended at more or less 11, 12 million years. Then the belt has been affected by rifting or by maybe something that you call Yadong or Kaligandaki Mustang. You have a angle normal fault, more or less perpendicular to the belt, extending the belt. Several structures like this. And of course, this kind of fracture are present also in the lower part, maybe the most in the higher part. But for example, if you give a look to the Everest area, you can find a lot of this fracture coming down up to the main central thrust. And so they, of course, deform the crust in a brittle way because it is already exhumed. So you found a lot of these transversal fault, and so that's very frequent. I don't know about the occurrence. Also, the main central thrust in some places show a brittle deformation inside the myelonate. There are one or two descriptions of this, but it is already in the same sense. And, I don't know if there are some normal fault deep into the south. I think there are some paper. Jit Mukherjee worked in Dauliganga Valley. That is an Indian guy, of course, working in structural geology, now editor of many books, many journals. But he worked a lot. He worked a lot on the brittle deformation at a small scale in the Himalayas. I think there are much more fracture than mapped because we are usually we think about the ductile deformation, but less attention to the fracture. But there are a lot. There are also out of sequence thrust that Samajit Mukherjee detected very well all over the Himalaya. Also, we found in the Mugu Karnali some out of sequence thrust above the HHD, maybe at 16, 17 million years. So the deformation is much more complex. I show you only one small pieces of the complex history. Some question? Okay. Okay. So thank you very much. Enjoy the lunch and see you after lunch.